Hi everyone, Dr. P here, and in this lecture video we're going to take a look at chemical bonding. So this is the first lecture for this chapter, and in it I want to talk about types of chemical bonds and then a little bit about some of the characteristics of things like covalent bonds in particular. In subsequent lectures, we'll look at both ionic bonds and covalent bonds in more detail. In particular, we're going to spend a lot of time looking at covalent bonds. All right, well, let's go ahead and get started then. And really, bonding is what chemistry is all about. It's chemical bonds. Understanding the nature of chemical bonds enables us to understand how molecules react and interact. So let's look at some types of chemical bonds, and the two main types are as we've talked about previously, ionic and covalent. Now, ionic bonds are electrostatic attractions between oppositely charged ions. So we'll say attractions between oppositely charged ions. Covalent bonds are where we have, let's say, electron pairs, and I'll abbreviate electron with an E minus, electron pairs shared between two atoms. So let's look at these in a little bit more detail. First, ionic bonds. At its simplest, an ionic bond will consist of a cation and an anion. So there's my positive cation, my negative anion. And then we've got some kind of bond, and then some distance in between them, which often we call a bond length, but that's more for covalent. So, these would be things like Na plus and Cl minus, etc. Now, these systems, like any system, will look for the lowest energy state. And so we can apply something called Coulomb's law. And if you've had physics, you may remember this. But the energy of an attraction between a positive and negative ions, actually any ions, you don't have to be positive and negative, the energy is some constant, 2.31 times 10 to the minus 19 joule nanometers, times Q1 times Q2 over R. And Q1 and Q2 are the ion charges. All right, so in this case, our R value is 2.76 angstroms. 1 angstrom equals 1 times 10 to the minus 10 meters. So this would be 0.276 nanometers. So our energy for NaCl then is 2.31 times 10 to the minus 19 joule times nanometers times plus 1 is the charge of our sodium, minus 1 times -1, which is the charge of our chlorine, divided by 0.276 nanometers. And this equals minus 8.37 times 10 to the minus 19 joules. My nanometers are going to cancel here. For a mole of sodium chloride, it ends up equaling minus 504 kilojoules per mole. So if we multiply this number, the minus 8.37 times 10 to the minus 19, if we multiply that by Avogadro's number, 6.02 times 10 to the 23rd, we end up getting minus 504,000 joules per mole, or minus 504 kilojoules per mole. So we see that this ion pair has a lower energy than separated ions, which is a good thing, or else, ionic compounds would just fall apart. So again, the ions in the solid sodium chloride are more stable than the free ions floating around by themselves in space. All right. Now let's contrast this, or compare this, or compare and contrast this with, let me get a new piece of paper here, what's going on with covalent bonds. So let's look at a diagram of energy versus the interatomic distance. So I'm going to have energy on this axis, and we're going to have some zero level here. And I'm going to draw this out. And this is R, our internuclear distance. And so look at H2, look at hydrogen. And so way out here we have a huge internuclear distance, so our hydrogen atoms are separated. And that means we have essentially, it maybe never quite gets to zero, it's an asymptote, but we have essentially zero energy. Now as we bring the nuclei closer together, the energy decreases until it reaches some point right down here. And if I, take a look at this here, this is my bond length. And so as we're going here, our H's are getting closer together. And then at this point, we have nice overlap in between so we have our overlapping H's. Now if I started to smoosh these together more, they'd get more and more squished together, and we'd actually get higher and higher energy. So these would be essentially on top of each other. So that's too high energy. So when things are separated, it's basically zero energy. When the atoms are right on top of each other, it's really high energy, not favorable. When the atoms have just the right amount of overlap, that's favorable, and that's our bond forming. And this happens to, our bond energy here happens to be minus 458 kilojoules per mole. And you don't need to know these values, but just understand that there is an associated value with a covalent bond forming. Okay. Now, In covalent bonds, let me rephrase, let me start over again. In covalent bonds, not all bonds are created equally. Not all bonds are between the same atom. So not all covalent bonds have equal electron sharing. So if we have something like HH, and here I'm going to use a line to represent a pair of electrons. This is a pair of electrons. I could draw it a few different ways. I could have, I could draw these little circles here, little balls with some overlap. I could have H with a pair of electrons in between, or I could have H with a line representing that pair of electrons in a bond. So these are other representations to represent my bond forming. So if we have two of the same molecule, we have equal sharing. But if we have if we have two of the same atom in a molecule, we have equal sharing. But if we have different atoms in our molecule, then we have unequal sharing. And those are called polar covalent bonds. So let's take a look then at an example here. And a good example is HF. And so the electrons are pulled more towards one side, the fluorine. We can indicate that with an arrow with sort of like a little plus at the end that the electrons are being pulled from. And then we can write a Greek letter delta, lowercase delta, with a minus to indicate a partial charge. That's what these deltas mean, partial charge. And so in the HF molecule, the hydrogen fluoride molecule, we have a partial negative charge on the fluorine and a partial positive charge on the hydrogen. And so this is a polar molecule. And it has a dipole moment, which is what this line represents. So we'll talk more about polarity later, but other dipolar molecules, other polar molecules that have dipole moments are things like water, ammonia, hydrogen sulfide, H2S. Other nonpolar molecules include carbon dioxide, methane, carbon tetrachloride. And so the polarity of a molecule depends on whether or not the bonds themselves are polar, but also how they are arranged. Now, what determines bond polarity? Well, it's determined by electronegativity. And electronegativity is the ability of an atom to attract shared electrons to itself. And so I will refer you to figure 7.6 to see basically a periodic table with different electronegativities on it. The general trend is, as you go to the right in the periodic table and up in the periodic table, you get more electronegative. So, and excluding the halogens. So fluorine is the most electronegative atom. And so, whenever you have fluorine bonded to anything other than fluorine, it's going to pull electron density towards itself. So these numbers are quantified. They were quantified by Linus Pauling, a famous chemist. Won 2 Nobel Prizes, one for chemistry and also a Nobel Peace Prize for his anti-nuclear warfare, anti-nuclear weapon advocacy. But anyway, so we'll talk more about this polarity later, but I wanted to introduce you to one of the aspects of covalent bonds, and that is the electrons are not necessarily equally shared. All right, so I've talked about types of chemical bonds, really basic, ionic and covalent. We looked a little more detail at ionic bonds and then at covalent bonds. And this is one of my favorite diagrams. So I have many favorite diagrams in chemistry, but I like this energy diagram of hydrogen. It's just kind of cool, showing that, yes, you get all this energy released when you make a covalent bond, which is a good thing, because if making bonds wasn't so favorable, then we couldn't make molecules and, well, we wouldn't be here. All right, well, I hope you're here with me next time as well. And in the meantime, stay safe out there.